Hi, good evening. This is the sixth lecture in IE 533, right? And last time we've talked about the LINGO sets, right? And compared to LINGO, the most powerful feature of LINGO is its ability to model very large system with using sets option, right? So today we are going to spend more time on the usage of LINGO sets with several more example problems, okay? Okay, so let's suppose the Las Cruces post office wants to hire full-time employees, and they requires different numbers of full-time employees on different days of the week, okay? The total number of full-time employees required on each day is given in this table. And the union rules state that each full-time employee must work 5 consecutive days and then receives 2 days off. So for example, an employee who works Monday through Friday must be off on Saturday and Sunday, right? The employee who works Tuesday through Saturday, for example, they must take off on the Sunday and Monday, okay? And the post office wants to meet its daily requirements using only full-time employees. That's our assumption. And we'd like to formulate a linear programming model that the post office can use to minimize the total number of full-time employees that must be hired, okay? And just let you know, before giving the correct formulation for this problem, let's just begin by discussing an incorrect approach, okay? So probably some people might think you could define decision variables x of I would be the total number of employees working on each day, I, right? So in that case, the I equals 1 means the Monday, I equals 2 would be Tuesday, and so on. So using this decision variables, you might think that the total number of full-time employees would be the total number of employees working on Monday plus number of employees working on Tuesdays and so on until total number of employees working on Sunday. Okay? And using this decision variable, probably you can think our objective function would be minimize the total number of employees, okay, working on each days, which is summation of x1 through x7, like this. And to ensure that the post office has enough full-time employees working on each day, you need to add these constraints. X of I is greater than equals the total number of employees required on each day. So for example, for Monday, x of 1 should be, okay, x of 1 is greater than equals 17, x of 2 is greater than equals 13, and so on, right? And x7 is greater than equals 11, things like that. And of course, you need to add the integer restrictions for each decision variables x of I. So with current decision variable, you may have complete LP formulation like this, right? However, there are at least two flaws on this formulation. First, the current objective function is not the total number of full-time post office employees, right? The current objective function counts each employee's how many times? 5 times, right? Not just once. For example, each employee who starts work on Monday works Monday through Friday. And all these people are included in the x1, x2, x3, x4, and x5. Is that right? And second, the variables x1, x2 through x7 are interrelated. And the interrelation between the variables is not captured by current set of constraints. For example, some of the people who are working on Monday, say x1 people, they will work on Tuesday, right? This means that x1 and x2 are interrelated. But our current constraints does not indicate that the value of x1 has any effect on the value of x2, right? And the key to correct the current formulation is to realize that our major concern is not how many people are working on each day, but rather how many people begin work on each day of the week, right? So with this in mind, we can define the decision variable x of I like this. That is, the x of I is the number of employees start to work on each day I. So using this decision variable, of course, the total number of full-time employees would be the total number of employees who start work on Monday plus number of employees who start to work on Tuesday and so on, right? Is that right? And because each employee begins work on exactly one day of the week, the current expression does not double count the employees, right? So when you correctly define the variables, the objective function would be as follows, which is the same as before, right? Minimize total number of employees who start work on each day, which is summation of x1 plus x2 plus x3, x4, x5, x6, and x7. Right? Is your mic fall on? Oh. Yeah. Thank you. Is that working?
Yes.
Okay. Do you know when did I fall off my mic?
Just a second ago. You're
Just seconds? Okay. Okay. Thank you. And what constraint do we need to consider? The same constraint, right? The post office must ensure that enough full-time employees are working on each day of the week, right? So at least 17 employees must be working on Monday, and 13 employees must be working on Tuesdays, and so on, right? Then who is working on Monday? to use a mouse. Okay. Hope it does work. Who is working on Monday? What about? Oops. Okay. Okay. What about x1? Is that right?
Yeah.
What about x2? No. What about x3? No. What about x4? Is that right? And 5? Is yes? What about x6? Yes, right? And x7 is also included. So everyone except for x2 and x3, right? Those two decision variables are not included, right? Is that correct? So these are the total number of employees who's working on Monday. Because each full-time employees must work 5 consecutive days and take off the following 2 days, right? And what else? Also, to ensure that at least 17 employees are working on Monday, for example, we require that the constraint x1 plus x4, x5, x6, and x7 is greater than equals 17, right? And adding the similar constraints for the other 6 days of the week, and the sign restriction, which is x of I is greater than equals 0 for all i's, will yield the following complete electric formulation, right? So if we consider Thursday constraint, for example, who is working on Thursday? Everyone except the employees who begin work on Friday or on Saturday, right? Because they will take the Wednesdays and Thursday and Fridays off, respectively, right? So this means that the total number of employees working on Thursday is x1 plus x2 plus x3 and x4 and x7, right? So it's this. Okay, then this is the input for LINGO using sets option. Let's talk about this one by one, okay? So using LINGO sets, first of all, we need to define the sets which is needed to solve the problem. So it defines the days of the week. We have 7 days, so we have 1.7 and associates with each with 2 quantities, which is in this case RQMT, that is the number of workers requirement, and start, that is the number of workers that will begin work on that day of the week, okay? And the end sets and the definitions of the sets. And next, we input the requirements for each day of the week. And next, we create an objective function by summing the total number of workers starting work on each day of the week, right? And next, for each day of the week, we create the constraints that ensures the total number of employees working that day is at least as large as the day's requirement. So for day I, for example, this part sum the total number of employees starting work over the value of j, satisfying j is greater than I plus 2 or j is less than equals I and j is greater than I minus 5. For example, for I equals 1, then this generates the sum which is start 1 plus start 4 plus start 5, start 6, and start 7, which is indeed the total number of workers working on day 1, which is on Monday. Now I'm going to show you how I got this part. Okay? First, let's consider the Monday constraint. Okay? So if I equals 1, which means it's Monday, j could take the value of 1, 4, 5, 6, and 7, right? So j is going to be 1, 4, 5, 6, and 7. So I would say j would be equals I, and for these values j is greater than 3, right? And 3 would be expressed by I plus 2 using I values. Okay, is that right? So in that case, I would say if I equals 1, then j equals I, or j is greater than I plus 2. Is that right? What about Tuesday constraint? If I equals 2, there is about Tuesday, j can take the value of 1, 2, 5, 6, 7, right? So for these two values, I would say j is less than equals I, but for these three values, j is still greater than I plus 2, okay? So if I equals 2, then we make a small modification from earlier constraint. J is less than equals I, or j is greater than I plus 2. Is that right? What about Wednesday? If I equals 3, so it's Wednesday, j can take the value of 1, 2, 3, and 6, 7. And still, those three values can be obtained by j is less than equals I, right? And these two values can be obtained by j is greater than I plus 2. Is that right? If I equals 4, that's the Thursday, j can take the values of 1, 2, 3, 4, and 7. The first four values can be obtained by j is less than or equals to I. And the last value, 7, can be obtained by j is greater than I plus 2, right? Because in this case, I is 4, right? So j should be greater than 6, which is only 7 is available. Because both I and j can take the values of 1, 2, 3, 4, 5, 6, 7. Only 7 values are available, right? What about Friday constraint? If I equals 5 is Friday, j can take the values of 1, 2, 3, 4, 5. So in that case, we just need j is less than or equals to I, right? What about Saturday constraint? I equals 6. J can take the values of 2, 3, 4, 5, 6. How would you get these values? J is less than or equals I and another constraint, because 1 should not be included, right? So that's why I would like to add one more constraint, that j is greater than 1, right? And this can be expressed by j is greater than I minus 5. In this case, I is 6. 6 minus 5 becomes 1, right? So if I equals 6, we do need a constraint. J is less than or equals I, and j is greater than I minus 5. Okay? Likewise, the last constraint, Sunday constraint, if I equals 7, j can take the values of 3, 4, 5, 6, and 7. Also, all these values can be obtained by these two restrictions, right? So if you combine all of these constraints for each values of I from 1 to 7, then it's going to be j is less than or equals I, and j is greater than I minus 5. Okay? Or, what other constraint do we need? Okay, j is greater than I plus 2. Okay? And this constraint is what you've got in this LINGO input. Okay? And next, this part ensures that the total number of employees working on each day is at least as large as the total number of needed on that day, which is requirement for each day I, right? So with this example, we've sent out the LINGO enables us to create 7 constraints by typing just one line, right? This is because LINGO allows us to group similar objects together into sets option. So in our example, such group would be the days of the week, right? Days. Next, to indicate that each variable must equal a non-negative integer, we've just used that gene operator like this way. Any questions so far? No? It's pretty easy, right? Okay, then let's consider the next example, chess snack food example. So in this example, the 4 brands of nuts are called the pawn, knight, bishop, and king. Okay, and each brand contains a specified ratio of peanuts and chestnuts. And this table lists the number of ounces of the 2 nuts contained in each pound of each brand, and the price at which the company can sell a pound of each brand. Okay. And chess has constraint, which is exactly the contract with suppliers to receive 750 pounds of peanuts per day and 250 pounds of chestnuts per day. Okay. And our problem is to determine the number of pounds of each brand to produce each day to maximize total revenue without exceeding the available supply of each nuts. Okay. Okay, then to solve this problem, first of all, we need to define the decision variable. How do you define the decision variable? What is our major concern? We must determine how many pounds of each brand must be produced, right? So how do you define the decision variable? Oops. So let's define the decision variable like this way. Let's say x of I represents total number of pounds. Of each brand produced, right? So let's say I equals 1 is pawn, 2 is knight, 3 is bishop, 4 is king. Okay. What is our objective? Our objective function would be maximize the total revenue, right? So using the information, cost information, our objective function would be maximize the course 2x1, 3x2, 4x3, and 5x4, right? Okay. And what constraint do we need to consider? The number of pounds of peanuts used must be less than or equals to the available peanuts, right? Supply of peanuts. Likewise, chestnuts. So it's going to be 15x1, 10x2, 6x3, and 2x4 is less than or equals 750. Is that right? Not exactly. You should divide by 16. You know why? We need to convert from ounce to pounds, right? Because 1 pound is 16 ounces. So we should divide by 16 on the left-hand side. Likewise, 1x1 plus 6x2 10x3, 14x4 less than or equals to 250, and the left-hand side should be divided by 16. Again, to convert from ounces to pounds. And this is the input for LINGO using sets. Okay? So first, we need to define the sets needed to solve the problem. So which sets are the primitive sets and which set is derived set in here? The primitive sets in these models are the nut types and the brands of mixed nuts, right? The nut set has single attribute, which is supply, that is the daily supply of nuts in pounds. The brand set has two attributes. They are price and X attributes, right? And price stores the selling price of each brand, and X represents the decision variables of how many pounds of each brand to produce each day. Okay? However, we need one more set in order to input the brand's formula. So we need a two-dimensional table defined on the nut types and the brands. So to do that, we need to generate a derived set, right, from cross of the nuts and brand sets. So in here, we have titled the derived set formula, right? And that's a single attribute, which is ounces, which will be used to store the ounces of nuts used per pounds of each brand. And because we have not specified the members of this derived set, LINGO assumes we want the complete brand set that includes all the pairs of nuts and brands, right? And of course, the end sets and the definitions of the sets. Operator, can you hear me?
Yes.
Oh, okay. Okay, now our sets are defined, so we can move on to the building of data sections, right? So in here, we can initialize the three different attributes. They are supply and price and ounces in the data sections. And with the sets and data specified, we can enter our objective function and constraints like this. First, we create an objective function of maximizing total revenue, right? And our current example has only one class of constraints. What is that? For each nut type, the total number of pounds of nuts, each nut used must be less than or equal to the available supply of each nut, right? So, any questions so far? Is that easy? Okay. Okay, then let's take another example. This is matching problem. Suppose you manage your company's strategic planning department, and there are 8 analysts in the department. And suppose your department is about to move into a new suite of offices. And there are only 4 offices available in the suite. And you need to match up your analysts into 4 pairs, okay? So that each pair can be assigned to one of the offices. And based on the past observations, some of the analysts work better together than they do with others. And in the interest of departmental peace, you'd like to come up with a pairing of analysts that result in minimal potential conflicts. So to this goal, you have come up with a rating system for pairing your analysts. So the scale runs from 1 to 10, with 1 for the best case, whereas 10 for the worst case. And the rating appears in this table, okay? So you have to decide how to make a pair of 8 different analysts. So we define decision variables like this way. Let's say x of ij equals 1 if we pair analyst I with analyst j, okay? 0 otherwise. So actually, this problem can be solved by integer programming, not the linear programming model, because we do include binary integer variables, okay, rather than just continuous variable. And our objective function is to minimize the sum of the incompatibility ratings. So we have to use the given table with incompatibility ratings, right? So it will be like this: minimize 9 times x12, 3 times x13, 4 times x14, 2 times x15, x16, 5 times x17, 6 times x18, right? And so on. And x23, 7, x24, up to 4 times x78, right? And what constraints do we need to consider? Each analyst is paired with exactly one other analyst, right? So let's say for analyst number 8, it would be x18 plus x28 plus x38 x48 58 68 and 78 equals 1, right? And for analyst number 7, it's going to be x17 plus 27 37 47 57 and 67 and x78 equals 1, right? Because in the given problem description, we have a table with incompatibility ratings with upper triangular matrix, right? So we'd better not to use the lower triangular values to save our computational effort, okay? So that's why I want to use x78 instead of x87, okay? Actually, this is the same, but we don't want to use this variable. So you can build up the same type of constraint. So, for example, for analyst number 2, you will have x12, the 23, 24, 25, 26, 27, and 28 equals 1. Likewise, for analyst number 1, it's going to be 12, 13, 14, 15, 16, 17, and 18 equals 1, right? So in our case, always the first subscript is less than the second subscript, right? To save our working space. And this is the LINGO input with using sets. So the first set of interest is a set of 8 analysts, right? The primitive set can be written as analyst and slash 1.8 and slash semicolon. And the next set we may want to construct is a set consisting of all the potential pairings. And this will be a derived set. We will build by taking the cross of the analyst sets, right? So as a first pass, we could build the dense derived set. Which is just the pairs, analyst, or it's just ST, right? And analyst, however, this set would include both, say, pairs ij and pairs ji, right? Because only one of these pairs is required. The second would be wasteful, right? And furthermore, each analyst cannot be paired with themselves, right? That is, pairs II should be excluded, right? The solution is to put a membership filter on our derived set, requiring each pair ij is the final set to obey. The condition j should be greater than I, okay? So that's why we have this part. Okay? So the start of the membership filter is denoted with this vertical bar character, right? This one. So this membership filter tells the second subscript. Last time I said this. The symbol and2 represents the second subscript, and and1 is the first subscript for a certain decision variable. So this membership filter tells the second subscript should be greater than the first subscript. Okay? And here we also concerned with two attributes of the pair set. They are rating and X, right? First, we need an attribute that corresponds to the incompatibility ratings of the pairings, right? That is the rating. And second one is the X, that is the decision variable, to indicate if analyst I is paired with analyst J, right? And the next, we simply initialize the ratings attribute using the data session. Actually, you don't need to make spaces like this, but it's just good for the readability of the model, okay? Because you don't have semicolon at the end of each line, LINGO assumes that this is just one set of data, okay? Because we do have a semicolon at the end of this number 4, right? And our objective is to minimize the sum of the incompatibility ratings of all the final pairs, right? This is just the inner product of the ratings and X attribute, right? Pretty easy. And I said, for this problem, we have only one class of constraints, right? That is, for each analyst, the analyst is paired with exactly one other analyst, right? The feature of interest in this constraint is the conditional qualifier, which is J is equal to I or K is equal to I on the SUM functions. So for each analyst I, we sum up all the X variables that contain I and set them equal to 1. So we guarantee that the analyst I will be paired up with exactly one other analyst. And the conditional qualifier, this one, this conditional qualifier guarantees we only sum up the X variables, which include I in its pairing, okay? And because we want X to be restricted to being either 0 or 1, we need to add a bin statement, to the X variable, okay? And as you know, a bin function restricts a variable to being binary integer, like 0 or 1, right? And to apply a bin statement to all the variables, the X attribute, we just add the add4 expression like this. And this parse-up solution appears like this from LINGO. So we can see the objective values. The total sum of incompatibility ratings from the optimal pairing is 6, right? And the corresponding optimal pairings are the 1, 6, 2, 7, 3, 8, and 4, 5. Okay? Well, we have plenty of times left over, but this is all for today. Okay? So from next time, I'm going to talk about the simplex algorithm for solving linear programming model. Okay? And let me know if you have any questions regarding homeworks or any materials that I've covered during the lectures, and stop by me or send an email. Okay? I would be happy to help you. Okay, thank you very much. I will see you next time. Bye.